So I realize I'm the only thing standing between you and your free time and your dinner. So I will endeavor to be as interesting as possible and hopefully give you a bit of information to take with you. My name is Victoria Hartwick. I'm also one of the contingent of people who work just down the road at CU Boulder. But I put up a very complicated title. But since this is an interdisciplinary conference, I'm going to try to take a bit of a step back and show how this work can be relevant to other planetary systems, but also within an astrobiological context. So with that in mind, I've tried to create 2 points as a sort of framework for the rest of this talk. The first of which is no man and no planet is an island, and we may need to really consider planetary climate within the context of a broader system. So when we typically think of planetary climate, we think of factors that are endogenous to that planet. We think about the composition of the atmosphere, any type of volcanic activity, the fraction of water to land. But it may be equally important to consider factors that are external to the system. So things like the evolution of the solar output, the impact on the short and long term of asteroidal impacts, and in the case of this research, what is the effect of a continuous flux of small particles at the top of the Mars atmosphere. And secondly, it's not always necessary to reinvent the scientific wheel, so to speak. And we can easily apply lessons from Earth climate research to other planets. So with that, I'll say that my research is primarily concerned with the microphysics of clouds, which is just a fancy way of saying, how do we determine where clouds form in the atmosphere and at what rate they form? And if there is one thing I could have you take away from this, it's that in almost all environmental conditions, clouds form heterogeneously, which means water vapor or some other gaseous component of the atmosphere is condensing onto a particle that's also suspended in the same environment. And that's what I'm trying to show here, is we have a particle, also called a cloud condensation nuclei or ice nuclei, on which ambient water gas can condense to form a cloud droplet and then grow to form a larger cloud droplet. On Mars, the only known source of ice or cloud condensation nuclei is surface mineral dust. For those of you who aren't familiar, I'll do a quick cartoon depiction of the cloud and water cycles on Mars. So you have wind blowing across the surface. If it's sufficiently strong, it induces a process called saltation, which just lofts dust particles into the air. At the same time, you have an exchange of water vapor seasonally from the polar caps and on a diurnal timescale from ground ice and absorbed water. Now, if you have suspended dust particles in regions of the atmosphere which are supersaturated with respect to water, you get clouds. Now, this seems pretty neat and tidy, and you may be wondering what I'm going to talk about for the next 6 to 7 minutes. And there's a big problem, and I made this slide red because it's a big problem. And that's when we look at the model simulations of cloud formation, how closely do they actually match the observations that we have? And the answer is not very well, especially when we consider the vertical distribution of water ice clouds in the atmosphere. And these are 3 examples of extinction versus altitude plots from the SpyCam instrument. So what you see on the bottom is extinction due to water ice particles per kilometer versus altitude from 10 to 70 kilometers above the surface. And I've put an orangish, yellowish line at 1e to the -4, because that's significant amounts of extinction. And this top plot is kind of what our models can reproduce, where we have a high amount of extinction near the surface that falls off by about 20 to 30 kilometers. But often, in these observations, we have higher altitude cloud layers that are completely absent from our GCM model simulations. And this can get really bad, especially when you look at this one, where you have clouds up to 70 kilometers above the surface. And the reason for this discrepancy between model simulations and observation is actually the main point about cloud nucleation that I brought up before, which is if you do not have an ice nuclei population on which to condense water, you won't get any clouds at all. And the current understanding of the Mars climate says that the only source of ice nuclei is surface dust. And it's really difficult to loft surface dust multiple scale heights to above 30 kilometers. So what do? We can actually look to Earth as an analog and look at high altitude clouds and see how they nucleate on Earth and what they nucleate on. So an example here, this nice picture, is noctilucent clouds, which are cirrus water ice clouds that form at the North Polar winter, which is a really cold region of the Earth's atmosphere that's similar to Mars conditions. And what these clouds are nucleating on is actually micrometeorite ablation byproducts, which just means the smoke particles that form when small micrometeoric particles impacting the upper atmosphere burn up. And these are some examples, if I can find my pointer, of micrometeoric particles that we've actually captured in the Earth's atmosphere. But there's a remote signature of this process, which is elevated ionized metals high in the atmosphere. So you see this elevation in sodium, magnesium, iron. And this signature has been seen on Mars as well. So we have direct evidence that this micrometeoric ablation process is happening on Mars. So the big question becomes, could these micrometeorites be responsible for the high altitude clouds that we see on Mars? And even a broader question, do we need to consider some process external to a planetary system to explain a fundamental aspect of that planet's climate? So to answer this question, I've used the Mars-CAM-CARMA general circulation model, and this was developed in partnership between NCAR and LASP. And this is kind of just a depiction of what GCM is and how it works. If you'd like more information, I'm not going to go into it here, but you can always find me. But what we did, and this is a nice artist rendition, we just added 7,500 tons of micrometeoric material, which sounds like a lot, but is a fraction of what we get on Earth every year. So 7,500 tons per year, and we just distributed it evenly in time and in space across the top of the model. And I'll show you some quick results. So here again, it's a similar, I apologize for all the lines, I'll try to walk through it. Again, we have extinction on the bottom, and the 1 to the minus 4 is marked by that line again, and again, altitude on the y-axis from 0 to 70. And these are just zonally averaged latitude bands. But what you'll see is when we have no micrometeorites, we do get some elevated layers, but the extinction is really low. And most of the high extinctions fall off below 20 or 30 kilometers. But the second we add this micrometeoritic source, you get elevated extinctions at about 30, but also these enhancements at high altitude around 50 and above. And again, this is a zonal average, so we're kind of smushing out some of these really high altitude interesting layers. But the takeaway point is when we add micrometeorites, we really enhance cloud extinctions at all latitudes and at all times. Secondly, there is an observed seasonal cycle in the haze top. The haze top is just basically the highest altitude in your atmosphere where you have significant extinction from clouds. There's a basic seasonal pattern that we see that corresponds with the orbit of Mars, where early in the year, which is here, when we're in northern summer or northern winter or southern summer, the haze top is low. And then when we warm up in the intense southern summer, the haze top rises. But the addition of micrometeorites generally raises the haze top globally. And you also get this interesting enhancement in the haze top over polar winter. And this corresponds with some observations. And there's no global coverage of the haze top. So I don't have a good data comparison, but you can maybe believe me when I say this is comparable. So finally, what's interesting to note is when we change the distribution of ice nuclei, it's not just where the clouds are, it also influences where the clouds are across the latitudes and longitudes, also how high they are in the atmosphere, and the radiative impact of these clouds, which can be really large. So to speak very generally, if you have fewer ice nuclei, you get larger cloud particles. As you increase the number of ice nuclei, you get smaller cloud particles. And this changes the way that it interacts with radiation. So when you have large particles, more of the light gets down to the surface and less is reflected to space. So that can have, obviously, a big impact on your climate. Also, the size of these particles changes the lifetime that clouds stay in the atmosphere, and whether you snow immediately upon falling or can move water and precipitation to lower latitudes. So if you look at the amount of water in the atmosphere versus time, when you add these micrometeorites, you can get water to reach to equatorial regions at a higher concentration. So I'll just briefly close by talking about the Mars paleoclimate and how this research applies to it. And this is kind of the big question in paleoclimate right now, which is, was Mars warm and wet or cold and icy? So this is just a depiction of those two competing hypotheses of early Mars. And what we found in very preliminary research is that having high altitude clouds that are large, with large particle sizes, you can sustain a warm Martian climate without artificially enhancing the atmosphere by adding different chemical components that we don't see real evidence of being there. So with this new model, we can look at how the vertical distribution of these water ice clouds influence the radiative environment, and also look at how the particle size and distribution will impact that. So hopefully that can get a little more information. So just to close, I'll try to summarize. Remember, clouds form heterogeneously, so you need an ice nuclei population to form clouds, or else you just get a supersaturated atmosphere. So the problem with the current generation of Mars general circulation models is that we can't loft ice nuclei to high enough altitudes to reproduce the clouds that we actually observe. But on Earth, high altitude clouds nucleate on micrometeorites. So we tried to look at that and see if we could reproduce these high clouds. And as it looks now, we can. So this is really promising and interesting work. So if you have any questions, since we're all talking about Iceland, this is me at one of the Mars analog sites. And so you can remember who I am and find me later. But you can also follow me on Twitter or email me. So we'll close there.
Questions? Oh, lots of questions.
So you mentioned that the tonnage of micrometeorites was fairly low. How did you come up with the number for that?
So this is just an extrapolation, basically, from Earth to the Mars orbit, based on what we know of the distribution of micrometeoritic material in the current solar system. But obviously, this is going to change with time. So if we rewind the clock to paleoclimate, it should be different. And there's actually a lot of complexity with the distribution of meteoritic material with season, potentially. So there's a lot of work to do here. But we've done different simulations that test, kind of parameterize and go through a space of this and do 0 to like 150% of that number.
I have two questions. So
yes.
The slide where you had the images of the different dust particles?
Micrometeorites, yes.
So the scale bar, you say 50 microns. Is that one particle or is that multiple like clumped together?
That's the conglomerate. These are really small. And usually that might be actually a particle that was captured high in the atmosphere prior to ablation. In the Earth's atmosphere, most of these are going to ablate completely, unless they're pretty large, and then coagulate to really like 0.01 micron size particles or smaller.
Yeah. Okay. Another question. So in your models, do you ever take into account the different mechanisms of heterogeneous ice nucleation? Because wouldn't like depositional ice nucleation happen like higher in the atmosphere versus like
What's nice about Mars is the entire atmosphere is really, really cold. So basically the same nucleation process that you'd see high in the Earth's atmosphere is basically everywhere. which is, so if anyone is an Earth scientist here, Mars can be like a nice sandbox to play around in.
Thanks.
So when you're looking at the paleoclimate of Mars, do you take into consideration that the sun should be fainter in
Yes.
the early solar system? Okay.
Yeah, I mean, that's basically why this icy highlands hypothesis originated, because I mean, you can't even really get Mars that warm now, and if you reduce the luminosity of the sun by that much, it's really difficult to warm the surface consistently.
I was wondering how long you expect these clouds to stay suspended.
It really depends on where they are. The polar clouds, for example, it's pretty supersaturated in that region, so they can grow really quickly, and then we get snowfall very quickly in that region. But if you change the parameterizations of the nucleation process, they can be smaller and stay suspended. So we see clouds that originate near the poles and are able to kind of drift down into the equatorial regions.
Okay, and then one other comment was, I know in exoplanets there's high altitude hazes that they're blocking. Do you have any insight into this mechanism as a possible explanation for that?
No, but I can wildly speculate, which would be to say that there's no reason why this micrometeorite material would be only in our solar system. So I think it'd be a potentially important factor to consider. And I think just as a point that we can't just look at these planets in isolation, and there may be other stuff going on.
Cool. I may have missed this. Do we know the grain size distribution of dust particles on Mars? Does it matter?
Yes and no. We know a fair amount about low atmosphere grain sizes. We know that there's a population of extremely small particles at high altitudes, but it's difficult to tell if this is dust or ice, so it's kind of hard to deconvolute that. And also these grain size retrievals are based on usually 2 wavelengths at most and a lot of assumptions.
I thought that might affect how much, how many nuclei you got into the air in the first
Yeah,
place.
it definitely. I mean, if you have a much larger particle than expected, it's going to ablate with at lower altitudes or less efficiently, which would change the distribution. But this is kind of exploratory at this point, and there's a lot of other parameterizations that we'd probably have to do first. But that's kind of touched in when we change the amount of meteoric material.
One more quick question.
So how do you determine how to distribute the micrometeorites spatially in your model?
Well, right now we just kind of follow Earth's example, and it's pretty uniform across latitudes and longitudes on Earth. There's some suggestion that there's distributions in time that vary, and there's definitely a distribution vertically, where you see an enhancement right at the layer of peak, or the altitude of peak ablation. But that's actually above our model top. So we've kind of skirted around that and just place it all right at the top. But that's another thing that we'd like to address in the future.
With that, thanks, everybody.